One of the problems that we're facing, and I want to just go through this rather briefly because it can be tackled in the same way by looking at particular codons and only at those codons. One of the problems we're facing is you would think that because the mutation rates have been established for a long time, that basically everything has remained constant and that everything should be at equilibrium. And what you would argue is that if I were to take again a set of codons, and again I'm going to take only those codons that end in C or T, so that's things like asparagine and so on, and I'll also be looking at the codons that have G or A in the third position. All right, now we must be careful here because although we say that's equilibrium, what do we mean? We mean that at this point, if I took all of these codons from every gene, now I'm going to talk about bacteria where I could have, say, 4,000 genes. I could just look at all the C and T codons and just count how many in each gene are C and in each gene are T. If I do that, I can get a ratio, and it's always expressed as T over C plus T, because if C is 0, you don't want to divide by 0. Computers don't like that. And in this case, the similar expression is A over A plus G. Right? Fraction of A, fraction of T. Well, let's just imagine an organism now that is where the equilibrium is 50-50. That is, as many flips, as many mutations are going from T to C in this neutral position as are going from C to T. And therefore, 50 would be the average, so we can look through the entire organism and we can, let us say, on average, if we count the number of T's, the number of C's in these positions of codons, that comes out to 0.5. All right? And if we do the same, this should be the same as this, and it is, it should come out to be the same value. Right? Now, if we do that, 0.5 here, we now imagine having a gene, just to give you a simple example, a gene with 100 such codons. All right? And the perfect example, perfect if it obeyed the average, is there'd be 50 of those would be T's and 50 of those would be C's. All right? Now we look at this gene again and let a mutation happen. So it's equal probability that a T will go to a C or a C will go to a T. So this gene would then change to be 51 T's and 49 C's. Right? So let's take that branch, because the other branch just grows us in the C direction, and you will see the answer in a moment. Now I'd look at this gene some time later, and I'll say, well, I've got a chance of flipping again, and as you can see, the chances are 51 to 49 is not much different from 50 to 50. So in roughly half the time, slightly more than half the time, this T will go back to being a C. Okay, because there's 51 of them. All right, but this C could go one more down again. with almost the same probability. All right. Now, of course, if we continue this process, by the way, this is called a Markov process, and we just let it run for a long time, we can actually get to situations, if we wait long enough, we can find examples in which this is 100 to 0. This is a well-known thing. So you will find extreme examples, even if the ratio is fixed and the system is in equilibrium. So you don't expect every gene to be identical. You will find things out there very easily that are 60-40. Right. Now, this gives us a way of actually looking at the organism directly through one diagram. Right? Because what I've said about the T's and C's applies equally to the A's and G's. And that means that if I now ask, what is the distribution of this, and I just measure the number of genes that are, let us say, that are 0.2, A, 0.4, 0.6, 0.8. I'm just abbreviating this. It can be done at a higher resolution. And this would be A over A plus G. And similarly, on this axis, I would have 0.6, 0.8, 0.10. What I find, of course, is that many of them are clustered around here. This is the average. And they clustered closer to the average. So if I look at all these numbers, I can draw a contour map of this. And it turns out that if it's at equilibrium, the contour map is symmetrical, like this. Right. Now what that tells you is this. This is in equilibrium, it's symmetrical, and the contour map is telling you that basically this process, which is moving genes up and down these paths, is the same because of the spacing of the two axes. Suppose this were a different process, not exactly the same, with different ratios, different frequencies of occurrence, what you would find in that comparison is that you would get an ellipse like that. But it would be symmetrical. And you would also find that to be the case if this average was different for those processes. That's just a scaling factor. Okay, so we can examine that and we can say, you're at equilibrium, so I can learn nothing from you. All right? And I do expect extreme cases, as I've shown you here, because that's just statistics. I will find things that look as though they came out of different organisms. For example, I will find things here that look as though they, in this over here, I'm finding things that look as though they come out of an organism whose average might have been 0.3, and over here I'm looking at things whose average might have been 0.7. But that's just to be expected, right? It doesn't mean that these were ported into this by horizontal transfer. In cases where there is horizontal transfer, it is amusing, and I just mentioned one, that if you do this with bacteria, you will find cases where there's a little island of things which are isolated from this, and this means this has a different origin, and of course sometimes it's moving towards this as it becomes dominated by it. Very well then, what does this mean for organisms like ourselves? Well, if I do the same plot for us, I just take the genes and I just make a plot like this. This is A over A plus G, and I do T over T plus G. I find that my contours look like this. I've got lots of peaks in this. And like this. I have it strewn out, all the genes strewn out on a diagonal. This means there's strong correlation of these genes, which are high AT, and these genes which are high T. Now remember, I have done this with protein molecules, with the genes encoding protein molecules, and I have looked only at these neutral positions. So how can I explain this? Because what this is telling me is the genome's no way in equilibrium, and what I'd like to know is what's the equilibrium that it's moving to. Well, if I plot this in one dimension, of course, what I get is just do this one for T plus C, then what I get is I get a huge sort of structure like that, going all the way from 0.1 to 0.7, T over T plus C. Now what I can do is I can take the mouse and I can plot his genes on exactly the same as this, on this kind of thing. And what I find is that he's a bit more compressed. I mean, this is very different structure, but effectively he doesn't occupy as much of the ground. This can be seen much better if I plot here the sets of genes of those that are 0.2 in the human. So of course those that are 0.2 in the human will come out on the diagonal. All right, so if I plot all the genes of the human against themselves with what they're in their abundance classes, I must get a straight line. It just shows me I've done my sums correctly. But if I do this to the mouse, the very same genes, I get curves like this. All right? Now, there is a very simple explanation of this, which you can see from what I told you before. Suppose, what is this crossover point? It's actually 0.28 for these codons. What does it mean here? Well, there are two hypotheses that you could entertain. What you could entertain is that the same process is going on in these two organisms, except the mouse is doing it faster. And what do you know? We already proved the mouse is doing it faster. So that will say these genes are moving upwards in that direction, okay, or did move upwards in that direction, and of course they're moving in the opposite direction. That is, the mouse genes are moving in the opposite direction at the other side. They have moved in the opposite direction. That arrow should be the other way around. Okay. Now the difficulty is that if you treat this seriously, which will explain why everybody's going to converge, you have to assume the human is moving up this. and it's moving downwards here too. And so what you say is that somehow all these genes got strewn out along this axis. We don't know the reason for it. And they are, so to speak, gaining normality in different rates. Except that it is impossible to fit this with a given rate. In fact, we have measured the rate. And this says that the rate could be part of this, but there's something else going on. And the fact that one could not measure it, one could not specify the rate or fill in the rate from this, showed that there was a different phenomenon going on. There's no doubt that the mouse is evolving, but there's no doubt also that it's doing it by a different process. Well, we can resort to our old friend by comparing all these genes and just ask for the genes that are turning, when I've seen that the mouse is changing C's into T's at the lower part of the curve, faster than the human is that a C to a T change or a T to a C change? So we have to do the comparison by going through those same genes with the cow genome and asking who occupied this place before. Then we can count exactly the probability that this changed from a T to a C. And we can also count the probability that in any case it changed from a C to a T. And what we can do from that is not use the existing fraction that we happen to measure, where we bin those genes in, but we could predict that if they are under this regime, this is the equilibrium they will ultimately reach if we let these processes run. Right, but the remarkable thing is, as you noticed, and it comes out of this, that if we do this, and so here are the genes again, 0.2, 0.4, 0.6, 0.8, and 1.0. And what I'm going to measure here is the predicted equilibrium for these genes. And I'm going to do this for both the mouse and the human. All right? And what I find here is that at the lower end of the scale, and of course there are fewer over here for the mouse, so it's not as accurate. So first I'll draw the human. This is 0.2. This is the predicted equilibrium. Okay. It's not scaled properly. Let's make this 0.2. 0.4, 0.6, 0.8. Now it's very interesting because if you look at the mouse, the predicted equilibrium over here rises. These genes are not very far off. It's almost a diagonal here. And for the mouse, it levels off at something like this. And I cut it off here because we have very few genes at the top end either. But this looks as though the mouse is aiming to be 0.35 A plus T. It looks like a very uniform process here. And that's just the ratio of the forward and reverse directions. And that this, after this very high GC area, seems to be the what the mouse is aiming to do. Now the human, interestingly enough, follows this curve for the early part. I just draw it separately. But then somewhere around here has a big inflection, and it is rising to be, it's aiming to be about 0.6 here. And remember, this is as a function of the GC composition. So if we were to look at a mouse gene over here, or well, let's look at it over here. Yeah, this is a good place to look at it. Here's a mouse gene, it has 0.6. Right? What we know is that a mouse gene with 0.6 is going that way, okay, because he's aiming to be 3.5. So he's moving in that direction. But a human gene at 0.6 is aiming, at 0.5, is aiming to go in this direction. Right? So the genes, once you've passed this point, these genes are moving up. The human genes are moving here to a higher point, whereas the mouse genes in this fraction are moving backwards. And that is why you can't fit this to a common curve. That's the reason. Now, of course, we now have a real tricky explanation. Having shown this, we can now say the equilibrium constant, that is where these genes are going to get to, seems to be different in the mouse and the human. And what does that mean? So we ask, which is the factor that is changing most? And remarkably, we can prove from this that if we look at GC, if we look at G plus C, we just add them together, that direction to A plus T. Remember, these are similar processes. That number, the probability that a G will change, seems to be relatively constant throughout this entire thing. What changes this is how much of these go back, which differs according to the composition of the DNA. All right, so a simple hypothesis to explain this is to say there is a repair process which is present in mice and absent in humans, which restores this reverse direction, that is, turns things back into A's and G's, and A to G and T to G, but seems to be absent in humans. So these genes here are not susceptible to it. But the question then is, why should it vary with the composition of the DNA? And there is a simple explanation for this, which I can't go into the details, but basically, if recombination was the driving force, then we would be able to make that account. In other words, if recombination varied according to this base composition, according to the genes with this base composition, then with the mouse ones, they would restore, but this would be an absent procedure. And this absent procedure in the human will mean that we just register all the G to C changes without restoring them here as a function of recombination. That needs to be proven, because if you can find genes that cannot recombine, it seems to be borne out from looking at genes on the Y chromosome which have no counterpart on the X chromosome. But there are only very few to test this on. But I now want to just finally conclude by showing you another interesting paradox, which I think has wonderful clues for looking at the past. All right, so I now want to just point out, to me, the most fascinating end result of this, which I'm still working on, and it is the following. Right? So I have all these genes here strewn out across a broad distribution with very high GC genes over here. So that is fraction of a fraction of, I'm going to now call it W over S. Okay, W over W plus S, where W is, of course, equals A plus T, and S equals G plus C. All right? So over here, these things that are 0.2, these are things where it's even 0.1. These are genes, and there's a certain number of them. So this is N, the number of genes. And so we can classify them in the human genome, in fact, in any genome, as to this distribution. Right? Right? And we now know that these two events are correlated, because if we do the double plot, we get a complete diagonal. It means there's history there. So what is this history? Who are these genes over here, and why do they differ from the genes over here? How do they differ? And when did all of this start? Right, so the hypothesis, and it still is a hypothesis, but there's very good evidence for it, is the following. And I'll just mention the evidence in a moment, but I'll first mention the hypothesis. The hypothesis is that genes over here are very slowly evolving in terms of their history. And the most rapidly evolving genes are over here. In other words, this is the original genome here. We'll show signs that it is the original genome here. Whereas this here has all been accumulated. Now that seems very odd, because this is all based on neutral changes. So how can we move them faster throughout a genome? And here there was a really hidden assumption, which I think we can now understand completely. When Kimura put forward his idea of neutral mutations, he put it forward in a model which assumed all the genes act independently of each other, like the classic balls in an urn or beans in a pot. That is, what happened to one gene didn't affect what happened to anything else. But what we know is that that's not true. Genes are linked, and what will happen with the genes when they are linked is any neutral changes that happen to be linked to a selective marker will be carried with a selective marker into the population. In fact, the term is called hitchhiking, which is exactly what it is. So, genes will move if at different speeds, even for the neutral mutations, provided they are linked to a selective marker. There are lots of equivalent explanations, such as you can also increase the probability that they'd survive when you reduce the population, and you will see that this is a way of reducing the population to a small number of ones, the ones who are going to amplify out of all proportion to the rest of them, because they're under selection. So we might expect that all these neutral changes that we've seen here came about because some genes were being driven in this direction faster than others, right? And the genome has had, so to speak, a distribution and hasn't had enough time to catch up, hasn't had enough time to catch up. So one of the questions we can really ask about this distribution is, in fact, can we find other evidence that this is a distribution that does affect in time? Right, now, I just tell you a fact, that if I look at genes over here, I find, if I look at, let us say, GGY, that means for the codons of glycine, how many of them terminate in a pyrimidine, which means it doesn't matter now whether it's C or T, and how many of them terminate in a purine. Then it doesn't matter whether these are A's and G's. So this has nothing to do with this process here. And of course, what I expect is for this measure, 0.5, if the genome is in equilibrium, that should be 0.5, because this should just distribute itself equally and doesn't affect it by anything else. What you find is that on the contrary, it is very biased to Y. It's about 0.7 here at this high GC, but the fascinating thing is it falls and then plateaus. There's another dip over here, but that can be explained, and I wouldn't worry too much about that. Well, if there is a process that is untangling this bias, then this fits very well, that the genes that are untangling it have been moving, and that these have undergone more events, so that this, at this point, this is in equilibrium. There's another remarkable thing which I can point out, and that is, as some of you, I hope all of you know, that in vertebrates, when a C occurs adjacent to a G, its mutation rate is increased. Okay? And there is a way of measuring this equilibrium. It's a bit too complex to go through because it gives us the measure for one of the processes that this enhances. It enhances it about 5-fold. All right? But the interesting thing is that over here, if I look at to the things in certain positions, the bias, there's no bias here. That is, there's no bias as compared to, let us say, CA. All right? And that the bias appears here and reaches an equilibrium, reflecting this process somewhere over here again. All right? So there's no bias, and it rises, and it reaches an equilibrium and stays that way. Again, pointing that to the idea that these genes moved, and that these, once upon a time, long ago, were over here, and that they've just moved across faster. All right. Now, the interesting thing is that if you go to this, this is a very interesting clue, because if you go to invertebrates, you do not find the CPG bias. This is a feature only of vertebrates. If you go to, say, look at Drosophila, look at invertebrate DNA, you do not see this bias. Right? So therefore, what we can ask is, if these genes really are still stuck in their invertebrate mode, because they've been evolving very slowly, they should actually have various other properties that reflect their invertebrate origin, or their origin a long time ago. And indeed, you can show that for several of the genes, the oldest ones here, that indeed they have codon ratios, codon usage ratios, completely different from the ratios over here, and that these resemble the ratios that you can find in the corresponding gene from Drosophila or any other available invertebrate. You can't use C. elegans, because C. elegans is at equilibrium. The whole genome is at equilibrium over there with a mean of about 0.66 on the scale. Now, what I would like to draw your attention to is that if this hypothesis is correct, then we've got something like the astronomers have here. We have these things which are talking to us and reflecting a structures that were present long, long ago, actually before the CPG event took place. Right? In fact, if you like, you could call it the CG shift. It's like the red shift. And that what we have here in the human genome are really fossil genes. Fossil genes, really, that tell us about things prior to the structure, prior to their origin as vertebrates, whatever they were at the time. So I think the fact that one can, by very careful analysis of our own genome and all the information in it, begin to understand the nature of these distributions, how we differ from others, comes in this case because of choosing the right measure and of really unveiling the hidden assumptions and trying then to find a theory that deals with it, and then seeking within the genome for evidence that is in there. Because if you do this work, you as a student of the human genome or the shark genome or whatever you're interested in are only interested in the germline. In fact, things that happened even 1 million years ago probably don't have a chance to register on the germline. You are not entitled, in fact, you can only invoke results from contemporary biology, if I can call it that. It's evidence neither for or against. For example, Drosophila has methylation enzymes, but there's no methylated C in its genome. The only way you could tell whether methylation is important or was important is to find evidence for that in the genome itself. In fact, I have shown you that the genes over here do not show the CPG effect, and so that is evidence from the genome itself that I can say. And long, long ago, this had it. Then there was the advent of the CPG effect as this process then moved. The other fascinating thing is that this study, which I call genome dynamics, it's just studying processes of change in here, has a very interesting connection to what's happening over here and over here. It has a very interesting connection to what is called the ergodic theorem, or one version of it in thermodynamics. What I'm saying is the following, that by following the average, the phase average, that is all of these properties, I could also say that that's going to be the time average. In other words, by looking at the average of all of these, by looking at this ensemble, I'll say I'd get exactly the same answer if I could take one of these genes and follow it in time over this distance here. Right? So I'm deducing, I'm reconstructing the past by something that I'm arguing for the moment, until there's secure evidence about this. I mean, I happen to believe that this is telling me about the dim distant past. So as you can see from this, if you think of this as a dynamic system, you can get an understanding then of how it all happened, so to speak, and that this data that we have, which you can get for free, it's all been sequenced, it's available for the public. If you can think up theories and you have even a PC is good enough to take a test set and test your theory. So people have often wondered, would there ever be home genomics where people could study genomes at home? And my argument is it's already there. And even amateurs like myself can actually try to solve very challenging problems by, I think, doing the research ourselves. Doesn't need much funding either. So I think that this will remain, and there's a wealth of data. It's accumulating all the time, and I think that this is a real challenge for us to meet. Thank you.